David Smith here with another Flipped Classroom math video. A few tips before we get started. Remember, you can always pause the video to make extra notes or write down questions for when we meet in class. Also, remember to pause the video when I provide an example. Work that problem, then start the video up again and see how well you did. You can also turn on the captions so you can see my words written below on the screen. You can also speed up or slow down the video if you wish. Remember to think hard, follow along, and bring your best brain to the next time we have class. Today's topic, probability review. As you know, we spent about 3 weeks in our probability unit, and I thought I'd put together a quick little video that goes over the high points of that. Remember, if there's any topics here that you feel a little shaky on, you definitely want to drill into the video for that particular topic. Okay, so we started off by comparing two types of probability. There's experimental and theoretical. Experimental probability was used to analyze situations where you couldn't just calculate right away. Things like that required us to gather data, like asking a group of high school students about a music preference, things like that. They're usually about populations or kind of strange events, like if you have a can that could land on the end or land on its side, what's the probability that it'll land on one or the other? We would throw that can a million times, record our results, then use that data to make a prediction about what would happen the next time we threw the can. So that's an example of how experimental probability works. Theoretical probability, which was the bulk of our work in this unit, probably 2/3 of it, uses calculations to figure out probabilities. So for that to work, we need situations that we know about, that we can analyze and use numbers to do our predictions. So that's usually about dice, about coins, about cards, and we did probability with spinners as well. And so these are objects that we can say things about, like a coin, 50-50 chance heads or tail. A die, a 1 in 6 chance of rolling a 3 on one die. Things like that. Both of these techniques are used to make predictions. And remember that whatever the technique you use, you're predicting. You don't know for certainty that the outcome you think might happen is going to happen. Okay, we organized our data during experimental probability into tables. This is a key point for figuring out probability questions. So let's say we did a survey. We interviewed boys and girls about whether or not they like juice or whether they don't like juice. Very simple question. And here's our results. 38 boys like juice, 45 girls like juice, only 3 boys don't, 6 girls don't. So when we have a table like this, we need to fill in our totals because those numbers are key for calculating probabilities. So to get the number of total boys, we just add these two up, that's 41. Total girls is 45 plus 6, that's 51. So now we know that we have 92 total people that we've asked this question. Now we can add up the likes juice. That's 38 plus 45. That would be 73. And let's add up the doesn't. That's 9. No, I boo-booed. 83. There we go. And this should also total up across the bottom. 83 and 9 does indeed make 92. That's how I caught my little mistake there. So check it out. Now my table's all full, and I can answer some questions like, what is the probability that the person we asked our question to is a boy? Okay, so that would be the total number of boys over the total number of people. So that would be 41 over 92. Pay attention, the instructions on a test or a quiz might ask you to put it into a decimal or a percent, in which case this would not be full points. I'm going to trust that you know how to divide 41 by 92 to get that. Let's do a little bit more complicated. How about probability of boy and likes juice? Okay, what would that probability be? So now we have to use only the boys that like juice. So that would be 38 out of 92. Now let's try another one, a little more tricky. What's the probability that it's a boy or likes? So that means all the boys, so that's going to be 41, but we also get to add the 45 girls that like juice because they qualify. It's boy or like, so that's going to be 41 plus 45 over 92, which is going to be 86 over 92. Okay? So now the questions are getting a little bit more complicated. I'm going to do a conditional probability question because that is covered a little later in this section. What's the probability that they like juice given that they're a girl? So it's like, and here's our notation, given that they're a girl. Okay? So what you have to remember is that the given that part is the bottom of your fraction. So given that they're a girl, how many girls do we have? We have 51 girls. So given that they're a girl, what's the probability that they like juice? That would be this 45. Okay, so tables come up all over this chapter, not just with experimental probability, but also with conditional, with exclusive, things like that. So you should be very comfortable organizing your data in tables and then using that data to answer questions like those. Okay, another set of tools that we use to analyze probability were grids, trees, and lists. These are 3 different ways to illustrate the sample space, and we have to understand the sample space if we're going to calculate probabilities. So I'm going to do one situation, and I'm going to show it with the 3 different techniques that we have. Die is rolled, and a coin is flipped. So we've got a 6-sided die, we roll that once, and then we flip our coins, heads or tails. So the first one I want to do actually is the last on this list. It's lists. These are pretty easy if you don't have too many possibilities in your sample space. In this case, we're going to be good with that. What we can get is we can get a 1 heads, 2 heads, 3 heads, 4 heads, 5 heads, and 6 heads. That's half the sample space because then we can also get a 1 tails, a 2 tails, a 3 tails, a 4 tails, a 5 tails, and a 6 tails. So here's our sample space, 12 possible outcomes, and they're each listed right here. Okay, so that's my list. Let's do a grid. So a grid only works with 2 events. If you have a 3rd event, you can't use a grid. So I'm going to do my grid like this. I'm going to put my die roll on the bottom. 1, 2, 3, 4, 5, 6. And I'm going to put my coin toss along the vertical axis. And then I just need a dot for every possible outcome. So each dot represents one possible outcome, like this dot here represents rolling a 4 on the die and getting a tail on the coin. So there's my grid. Let's do a tree. Now some people find trees to be the most challenging, and I think in some ways they are. They also are the most powerful for analyzing complicated situations. So let's do that. 1 die is rolled, so we do 6 branches because we have 6 possible outcomes. We have a 1, a 2, a 3, a 4, a 5, and a 6. And then what we like to do on our trees is we put the odds on the tree. We put the probability. So this is 1/6. In fact, everything here is 1/6. Okay? Now that's the probability for each possible branch on our tree. We roll the die, we could get 1 out of 6 outcomes. Now we continue, so this is the die roll. So now we continue with the coin tossed. And we're going to have just 2 on each of these. Heads, tails, heads, tails, heads, tails, heads, tails, heads, tails, heads, tails. And there's a little bit of an art to being able to draw a tree so that you have enough room by the time you get out to your last set of branches. The trick is, my trick is, make sure that your first set is wide. Use all the space you have. All right, now these are probabilities are just 1/2 each time. I'm not going to keep labeling. Oh, I better. Let's just be thorough, right, guys? I'm always telling you that in class, so let's just do that. Okay. Now, one of the cool parts about a tree is that if you wanted to figure out what is the probability of first rolling a 2 and then rolling and then flipping a tails, you just follow that path. So 2 tails, and then you multiply your probabilities. It's 1/6 times 1/12. That would tell you the probability of that. So you can see this is kind of like a really nice setup for calculating all kinds of different probabilities. Let's look at some similarities in these. There are 12 outcomes in our sample space. We have 12 items on our list, we have 12 dots on our grid, and we have 12 ending pathways on our tree. That should always be. Okay, let's take a look at using a tree to calculate probabilities for a different situation than the last one. Here, I've got two bags of marbles, bag A and bag B, and you can see that A has 4 blues, 2 reds, and 1 yellow, and B has 1 blue, 3 reds, and 2 yellows. And problems like these typically involve picking a marble out of one bag and a marble out of the second bag. So I've drawn my tree to reflect that. This is bag A, and this is bag B. So all of these branches here deal with that first draw coming out of bag A, and then all the sub-branches that come off the first relate to drawing a marble out of bag B. Okay? So, let's take a look at the probabilities. I just put them on the tree itself. Drawing a blue from A is 4 blues out of 7 totals, so 4/7. Drawing a red out of A is 2 reds over 7 total, 2/7. And finally, drawing a yellow, there's only 1 in bag A, so that's 1/7. So let's take a look at bag B on the first branch, on the blue from A branch. What's the chance of getting a blue from bag B? I wrote 1/6, let's check this out. Yeah, there's only 1 blue marble, and there's 6 total in bag B, so that's 1/6. Red from bag B, I wrote 3/6, and indeed, 3 reds out of 6 marbles, so that's 3/6. And then finally, yellow in bag B, I have 2 yellows out of 6, so I wrote 2/6. Now, sometimes it's a little easier to not reduce your fractions on your trees. Sometimes that helps with cross-canceling later when you're multiplying some of the probabilities. Okay, so if you've done this and you've built your tree, now you're ready to answer some probability questions using that tree. I've got 3 stacked up here for us to look at. So let's look at that first probability. What's the probability of getting blue first, red second? We multiply our branch. This is 4/7 times 3/6. 4/7 times 3/6. That's going to be 12/42. Now you can apply your calculator and find out what the decimal or the probability, the percent chance of that happening really is. Okay, so now we're going to ask for a blue and a red. Notice how it's not specifying the order, so there's 2 ways to get that. Actually, that's one of them already, blue-red. So that's blue first, red second. But we can also get a blue and a red by drawing the red first and the blue second. So it's these 2 possibilities, and we have to add them up. Okay, so let's take a look. We know what this one is already. This is 12/42. We calculated that up above. So I'm just going to rest on that. This one we need to figure out. So let's multiply 2/7 by 1/6. That's going to be 2/42. So this is going to be 14/42. So to summarize, if you have 2 branches on your tree that get you the result you're after, in this case it was just a blue and a red without regard for order, then you calculate the probability of each branch by multiplying, and then you add the results of each branch together to get the total probability. Okay, let's do this last one. This is the most confusing. At least 1 blue. So there's 3 pathways to get 1 blue at least. Draw it on the first one. You're there, okay? So we're going to add this one up. Now 4/7, I noticed over in my fractions I'm using 42 as a base a lot, so I'm going to convert 4/7 to 42s, and that's 24/42. Okay? It doesn't matter what happens next, because whatever we get, we've got at least 1 blue. We can get 2, and that's not a problem. We're allowed to, because it says at least 1. If it said exactly 1, then we'd have to do some more math here, but we don't. Okay, so that's our first branch, right here, actually stopping right there. Second pathway, that's going to be red first, then blue. That's going to be 2/7 times 1/6, which is going to be 2/42. And our last pathway is yellow first, blue second. So that's 1/7 times 1/6, which is 1 over 42. Now my fractions all have common denominators. I can add their tops. 24 plus 2 is 26, plus 1 more is 27 over 42. And there you have it. Okay, to finish this video, I'd like to review the equations that we developed along the way in our probability chapter. So the first thing we talked about was this equation. Probability of E is the frequency over the trials. Do you remember what we called this? This is the relative frequency. So relative frequency. This is basically the definition of relative frequency, this equation. Okay, so this is like flipping a coin 50 times and recording how many times you got head over the total number of trials, which would be 50 in that case. So we have another more formal way of looking at this. The probability of event E is the number of outcomes corresponding to E over the total outcomes in the sample space. So this is with theoretical. So this would be using a die to say the probability of a 6 was 1 out of 6, because there's 6 sides and there's only 1 6 in the sample space. So outcomes corresponding to rolling a 6 is just 1. Total outcomes in sample space, there are 6 sides on a die. Okay, we came up with another equation for compound independent events. These are 2 events that can happen together or in order, but they're independent of each other. So whatever happens in one does not affect what happens in the other. So compound independent events. The math is pretty simple. If you want the probability of getting both of these things, then it's just the probability of the first one times the probability of the second one. Pretty easy math. Let's do an example just to make sure that's clear. What's the probability that I'll roll a 2 on a die and flip heads on a coin? So the probability of rolling a 2 is going to be 1 out of 6, because there's 1 2 on a 6-sided die. So that's 1 out of 6. Flip heads, that's a 50-50 chance, or 1/2. So that's going to be a total of 1/12. So the probability of rolling a 2 and flipping heads in this compound event, that's 2 independent events, is 1/12. Okay, let's look at compound events that are dependent. So this is a little bit different. The equation, if you want to know the probability of event A and B happening, it's the probability of A happening times the probability of B given that A happened. So what that means is that when A happens, that's going to change the probability of B. So it's not going to be just the probability of B alone, it's going to be the probability of B given A happened. And we have a way of writing this, that's this. Probability of B, vertical line A. So what that means is the probability of B given that A happened. So a little bit of notation there. Okay, let's do an example for one of these types. I've got a standard deck of playing cards. 52 cards, 26 red, 26 black. That's all you need to know to analyze this problem. Okay, so the probability of drawing 2 red cards. So it's just the probability of event A times B given that A happened. So the first one is going to be 26 over 52. That's the probability of drawing a red card out of a deck of cards. Now, what we're going to need to do here is multiply that by the probability of the next draw, which is again drawing a red card, but given that A happened. So that means now that there's only 51 cards left in the deck, and there's only 25 red ones left in there. Okay, I just pulled out my calculator and did the math on these 2 big fractions, and I got 0.245 or 24.5%. Okay, so that's how you would do a probability equation with compound events that are dependent on each other. Okay, let's take a look at some mutually exclusive events. This gets a little tricky, but I think you can get there. We've actually been doing some mutually exclusive events already, just we haven't been talking about them like that. Okay, so mutually exclusive events are things that can't happen at the same time. If one thing happens, the other one cannot. So the probability of event A and B happening, if they're mutually exclusive, is 0. Okay? So it just can't happen. I'm going to get into an example in a minute so you can see what that might look like. When they're mutually exclusive, the probability of one or the other happening is fine, and we can calculate it. It's just the probability of the first one happening plus the probability of the second one happening. Okay? So let's do a couple examples with these that will help you see how this works. I'm going to use a deck of cards again. What's the probability of picking one card and having it be an ace and a 7? It's not possible. If the card is an ace, it cannot be a 7. There's no way. Or if the card is a 7, it cannot be an ace. So this is mutually exclusive, so the probability right there is 0. Okay? However, if we rephrase our question to say, what's the probability of pulling an ace or a 7, we can do that. It's just the probability of an ace plus the probability of a 7. So we know from a deck of cards that there's 4 out of 52 aces, and there's 4 out of 52 sevens. So this is 8 out of 52. Okay? And that's going to reduce down to 2 out of 13 if you want to reduce it. And then of course you can get out your calculator and turn that into a decimal if you like. If you still have questions, write them down now and bring them to our next class. You can also watch the video again and perfect your notes. Finally, if you enjoyed watching my video, please click the like button down below. And if you'd like to help me grow my YouTube channel, please click subscribe.